Hello, welcome back. In this segment, I will answer this question. What is the probability that a random odd k-bit number is a prime number? All right, from the prime number theorem, we know that the number of primes not exceeding the number n is n over log n to the base e approximately. This is approximation, okay? Although I put equal, you should assume it's an approximation. Okay, this is a nice fundamental result from number theory. We can leverage this to answer this problem. Okay, let me denote P of k as a probability that a k-bit number is a prime. I'm assuming k-bit number is an odd number because all of the primes are odd except number 2. Okay. First of all, recall that how many possible k-bit numbers are out there? Just 2 power k. If I asked you to write all the 3-bit numbers, you would write 000 all the way until 111, which means there are 8 possibilities. So how many possibilities? 2 power k possibilities. Now we can directly apply this prime number theorem here. That means we have pi of 2 power k, right? But remember, this pi of 2 power k also includes numbers that are not k-bit numbers. So we need to only limit ourselves to k-bit numbers, not not numbers that would take k minus 1 or k minus 2. Everything must start at the first bit must be 1. That's the meaning of a k-bit number, right? That means we need to get rid of numbers that are not k-bit. Okay, and how many of those numbers do we have? 2 power k minus 1, right? I mean, just if you plug a number k to be 3, it should be clear for you why I do pi of 2 power k minus pi of 2 power k minus 1. If k is 3, there are 8 possibilities, but those 8 possibilities are not all of them 3-bit, right? There are half of those that are actually starting with 0. So we don't need those. That's the reason why I'm subtracting by 2 power k minus 1. That means we will get rid of the remaining 4 numbers that are just requiring only 2-bit in the case of k being 3. All right, that's basically it. Now we need to divide this by how many possible k-bit numbers are there. We are only limiting ourselves to odd k-bit numbers, right? So remember, there are 2 power k minus 1 possible k-bit numbers. And we are limiting ourselves to odd. That means there are 2 power k minus 2 in the denominator. Okay, let me explain why I'm putting 2 power k minus 2 in the denominator. How many k-bit numbers are there that are odd? There are 2 power k minus 1 k-bit numbers, and half of them are even, half of them are odd. That's the reason why I have to put 2 power k minus 2. Okay, wonderful. And why did I subtract pi of 2 power k minus pi of 2 power k minus 1? The reason is this, that we are only interested in k-bit number, okay? And how many k-bit numbers are there? 2 power k possible numbers are there. But we don't want the leading bit to be 0, okay? If leading bit is 0, that number is not k-bit number, okay? That's the reason why we will leave out those numbers, okay? That means we know for sure our most significant bit is actually 1. That's basically the idea of this arithmetic. Okay, and now if you plug in a pi of 2 power k means 2 power k by log 2 power k to the base e and so on, which is also to the base e, which is approximately 3 over k. Okay, just a rough approximation. So what it means is that suppose your k is say a 30-bit number, then we can expect 1/10 is the probability that a random 30-bit number is a prime. Okay, that's the meaning of this. It becomes more interesting if we start increasing the k. Let's say k is a 1024-bit number. Then what is the probability that a random odd k, a 1024-bit number is a prime? Is 3 over 1024. Very, very tiny probability. Okay, that's the important fact that comes straight from the definition of the or rather the application of the prime number theorem that I have put it in the box. Pi of n denotes how many primes are there from 1 through n, including n. So it's an approximation. It's nothing but n over log n to the base e. We use that result to measure what is the probability that a random odd k-bit number is a prime. Okay, we found out that it's nothing but 2 over log 2 times k. In the denominator is k times log 2. which is nothing but 3 over k approximately. Okay, that's a very interesting result that we will leverage later. Thank you.